Okay. All right, so this is our last topic in Chapter 9. And we are finished with it, and to me it's the hardest unit that we cover overall. I do think that it has gone much better this time, and hopefully you guys will have some success when it comes test time. So the last thing we're talking about is interval of convergence, and I've been referring to this along the way, right? We come up with these Taylor polynomials, but I need to know where they're good. Okay, I need to know the interval on which the polynomial and the real function would match up, right? Because that's what we've been doing, is writing out Taylor polynomials that mimic these functions. And I need to know how good those Taylor polynomials are. Okay, so that's what today's topic is. So a power series in X can be viewed as a function of X, f of X equaling, sorry, this is 0 to infinity, okay, where f of X is the sum from n equals 0 to infinity of a sub n x minus c to the n, right? That's just describing a power series. That's all that's describing. Where the domain of f is the set of all x for which the power series converges, okay? So the domain of the power series will be the values of x where the polynomial does what? Converges. Okay? So determining the domain of the power series is referred to as finding the interval of convergence. Right? And then here's just some bullet points. One of the following statements with regard to interval of convergence must be true about the power series. Okay, so one of these three things has to be true. The series converges only at the center C. What does that mean?
It has like between the actual graph and our Taylor polynomial, there's only 1 point in common.
Very good. There's only 1 point in common between the series and the Taylor polynomial, right? And that point is the center. And that would make sense that it would be the center, right? Because that's where we're building it, okay? So probably the easiest visual there would just be to think about a tangent line to a curve, right? A tangent line to a curve, it only shares what? 1 point, okay? So the series might converge only at the center C. It might converge for all x. What did we find the other day as we were graphing the Taylor polynomial for sine and cosine of x? Right, the more terms I added, the what? The closer it got, right? And what we'll find today is that we can show that it does in fact converge everywhere, okay? And then the last option is there exists a real number r that is greater than 0 such that the series converges when x minus c is less than r, the absolute value, and diverges when the absolute value of x minus c is greater than r. This number r is the radius of convergence of the power series. Okay, so here's the best way to think about that. It's easiest with a picture. So here's the center, right? This would be a radius, and this would be the radius, and this would be the interval of convergence. Okay, so we're building it around the center, right? That's where I start my polynomials at a center. And my interval of convergence is how far I get away from the center and my polynomial still fits, right? So what we're saying is that it can only be good at the center, in which case the radius of convergence would be what? 0, right? And when we mean radius, we truly mean like the distance from the center, just like you would in a circle, okay? So we're truly talking about the distance we are from the center. Yes, sir?
So the more terms you add to a Taylor polynomial, the bigger the radius gets.
If it converges for all x. I mean, Not necessarily. You could add as many as you want, you could add as many terms as you want, and it still might only converge at the center. It might only be good at the center. So that isn't necessarily what we're saying. We're saying this though, that the radius is the distance from the center, and in that radius, your Taylor polynomial will converge. Okay, so I can either have a radius of 0, which means that I converge only at the center. I could have a radius of infinity. That means that it converges everywhere, right? Or I could have a set interval of convergence. Like it might be good 2 units to the right of the center and 2 units to the left of the center, right? And it has to be symmetric because we're talking radius. So if you're centered at 0 and your radius of convergence is 2, what's your interval of convergence? -2 to 2, right? If you are centered at 1 and your radius of convergence is 3, what's your interval of convergence? -2 to 4, right? Okay. So we can have an infinite radius, we can have a radius of 0, or we can have a radius that is a set number. Yes, sir, Nick?
When we're talking about radius, are we talking about arc length? Like that value that the radius is, I don't know how to word it. Is that just arc length? Like from
Or is it just like
from
the x
where
value?
your center is, like to where it stops?
Well, I will tell you that in a series, the radius, and this is going way beyond the scope of the course pretty much, but it really is the radius of the largest circle that the series would fit in. But we're not going to go there just yet, okay? All right, so we know that a series is a sum, right? The series is the sum of a sequence, okay? And what we have learned in this part of chapter 9 is that we can write Taylor polynomials that mimic the functions that we're dealing with. And those Taylor polynomials can converge at the center only, they can converge everywhere, or they can converge on a set interval, okay? So now, and then we actually just covered this, the series converges only at C if R is 0, the series converges for all x if R equals infinity. To determine the radius of convergence, we use the ratio test. Okay, the ratio test. Do you guys remember what the ratio test is? What's the ratio test? Let's write it down here.
It's like the n plus 1 divided by n.
Yep, the ratio test is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, right? Okay, that's your ratio test. If this is less than 1, what happens? Greater than 1? Diverges. Equals 1?
Can't tell.
Yep, inconclusive.
Would that be a ratio?
Does not exist.
Wouldn't you wouldn't ever think about using the ratio test if it was 1, right?
Well, if you're asked to find the radius of convergence or the interval of convergence, you're going to automatically use the ratio test. But if you get 1, you just don't know anything. Okay? Now, okay, so back up a little bit to the questions that I was asking you a while ago. I said, if your function is centered at 2 and you have a radius of, if your function was centered at 0 and you had a radius of 2, what's the interval of convergence? What'd you tell me? You told me -2 to 2, okay? You're almost there. -2 and 2 are endpoints, and those endpoints must be tested for convergence.
So you know if it's a closed or open interval?
Correct,
Oh, yeah.
so that I know whether it's a closed or an open interval. So here come all the tests from 9.2 to 9.6, right? Power series tests, geometric series tests, P-series tests, or interval tests. So remember I kept telling you we're going to use those tests?
Now.
We had to learn them, right? Now we're going to use them, and that's the last bullet point here. To determine the interval of convergence, we must test the endpoints of our radius of convergence using any of the other tests for convergence or divergence we have previously learned. Okay? So here we go. We can do some examples. Best way to show you. Okay, so the directions for all of these examples are find the radius of convergence and the interval of convergence for the following series. As soon as you see those words, find the interval of convergence, radius of convergence, your brain is going to go to ratio test, right? So I'm going to do the ratio test. And I know that the ratio test says to do the limit as n approaches infinity of the absolute value of a sub n plus 1. So what does that mean to do? Wherever there's an n, put an n plus 1. And I divide that by, yep, which is n factorial over x minus 3 to the n. Okay, so tell me about this n plus 1 factorial and the n factorial. What's that simplify to give me? It leaves me an n plus 1, right? Because this is the same as n plus 1 times n minus 1, right? So that's the same as n factorial. And then what about these? It's just x minus 3, right? So I'm supposed to do the limit as n approaches infinity. What's this thing going to approach? Infinity. Okay, so since infinity, now the ratio test says what? Right, so since infinity is greater than 1, the series diverges everywhere except x equals 3. Okay, so this asks me to find the radius of convergence and the interval of convergence. So the radius is what? 0. The radius is 0. Right? Because it only converges at the center.
And the interval would just be.
Right, and it converges at x equals 3 only. Okay, so you're going to have to do some thinking here, right? Because you're going to get infinity for this answer, and that might lead you to think that the radius is infinity, and it's not. Okay, this is just the ratio test. This is just producing the results of the ratio test, which tells you about convergence and divergence.
So it's always going to converge at the center, right?
It will always converge at the center, always. But it might converge everywhere, and it might just converge in this area around the center. Okay, let's look at the next one. First of all, tell me what this is. Okay, more specific than that. Yeah, this is sine of x. right? Isn't this sine of x?
Yeah.
That is sine of x. That is the Taylor series for sine of x. What would you expect this to do? Converge for all x, right? That's what you would expect. Okay, so let's go through the process and see. Okay, so the ratio test. And notice I'm writing the word ratio test so that I'm reminding myself that's all I'm doing right now is determining convergence and divergence of this thing. And then if it converges, then I can talk about where it converges. If it diverges, it's only going to converge at the center. Okay, so I'm going to do the limit as n approaches infinity. Since I'm doing absolute value, what can I leave off? The alternating part, right? I don't need to include that. It just clutters things up. Okay, so I'm supposed to insert an n plus 1 everywhere there's an n, right? And I'm supposed to divide that by the original, which would be the same thing as multiplying by the reciprocal. So I'm going to clean this up a little bit. So this is going to become x to the what? The 2n plus 3. And what's this going to become down here? 2n plus 3 factorial. And then this part just stays the same, right? Okay, so let's do the x's first. What's going to be left? An x squared in the numerator, right? And then let's talk about this. This 2n plus 3, it goes 2n plus 3, then what? 2n plus 2, then 2n plus 1, and aha, I can stop there, right? Because that's going to cancel out. So I'll be left with 2n plus 3, 2n plus 2 in the denominator. Yes, and the limit of this as n approaches infinity is 0.
So it converges.
Yeah, so since 0 is less than 1, the series converges where? Everywhere.
So if you get 0 or if it's less than 1, it converges everywhere.
Yeah, if it's 0 though, if it's 0, you don't have to bother with the x at all. You're going to see in the next example where you get something other than 0 and there's more work involved. But it will still be less than 1. Okay? So, well, it's going to have a variable in it. That's what will happen. You'll see in the next example. Okay, so the series converges everywhere. So the radius is what? Infinity. And the interval is negative infinity to infinity. Yeah, there are no endpoints to test in that one, right? How we doing? Doing okay? All right. Will you notice that there is a whole page here to do this problem? I have left you a whole page. Are you ready? Ready? Okay, directions are the same. Determine the interval of convergence and radius of convergence for this series. As soon as you read those words, you need to think ratio test.
Get rid of the alternating, right?
Yep. So the ratio test says to do the limit as n approaches infinity of x minus 5 to the n plus 1 over n plus 1 to the 2 to the n plus 1. And then I want to multiply that by what? The reciprocal, right? N 2 to the n over x minus 5 to the n. Okay, so I'm gonna list my n's first because I'm gonna have an n in the top and an n plus 1 in the bottom, right? And then what about the 2's?
There's going to be a 2 in the denominator.
There's gonna be a 2 in the denominator. And what about the x minus 5's?
It's gonna be 1.
Yeah, there's gonna be 1. I heard somebody say it. There's gonna be 1 in the numerator.
Now we have to find a way to test that.
Well, here's the thing. What is the limit of this as n approaches infinity?
The bottom's on is gonna be 1. Is that 1 contra?
It's going to be 0.
Well, you could. Okay, so here's the thing. If you can't, so here's what I'm going to do. I'm going to remove everything that's not an n, and I'm going to pull it out front of the limit. Okay, so I'm going to do this. I'm going to do x minus 5 divided by 2. Limit n goes to infinity of n over n plus 1. I'm really, really hoping that you don't have to use L'Hopital's rule at this point for this problem. I mean, you can. It's how you're getting the answer. But what's the answer to that? 1.
Oh, sorry.
If you have n, right, and n is 1,000, and you divide it by 1,001, or you have a million divided by 1,000,001, I mean, we're getting really, really close to what here, people? 1, right? Okay. All right. So, but you can do L'Hopital's rule. All right. So the derivative of the numerator is 1. The derivative of the denominator is 1. So the answer is 1. Okay. So what's left here? X minus 5 over 2.
Is that like 1 times x minus 5?
Yes.
Okay.
It's 1 times. Sure. Okay. Now what has to be true about this? And sorry, I should have put that in absolute value bars. What has to be true about that in order for this thing to converge?
That has to be less than 1.
Yes. So x minus 5 over 2 must be less than 1 in order for the series to converge.
The absolute value doesn't have to be the absolute value of.
Yes. Okay, are you with me? This must be less than 1 in order for this whole thing to converge. Yes? Okay. So now I need to go and I need to solve this absolute value inequality so that I can figure out my interval, right? So therefore, x minus 5 over 2 is less than 1, and x minus 5 over 2 is greater than negative 1, right? That's how you solve an absolute value inequality. So multiply both sides by 2, add 5. So x has to be less than 7. And x has to be greater than 3. Okay, so here's what I know at this point. But I have to check the endpoints of x equals 3 and x equals 7. Okay, you guys with me? Is everybody caught up? I need to make sure you're caught up before I start this next part.
Are you there? Are you there?
You hurt his feelings, Sophia. Come on, tell him.
Thank you so much.
Right now she's checking.
Okay. All right, so remember, this is your series, right? The series is from n equals 1 to infinity of negative 1 to the n plus 1 over n times 2 to the n times x minus 5 to the n. This is the original series, right? So I have to take this series and substitute in what? 3 and 7 in place of x. Those are x values, right? Okay. So I'm gonna start two different problems here. I'm gonna say, okay, at x equals 3. I now have the series from n equals 1 to infinity of negative 1 to the n plus 1 over n 2 to the n, plug in 3, right? 3 minus 5 to the n. Which is negative 1 to the n plus 1, negative 2 to the n over n 2 to the n. Any thoughts on what you want to do?
What is it?
The
The
Or
we're only using the exponents.
Wait, that's negative 1 to the n. Ratio.
Okay, so what if I'm really close to being able to cancel out 2 to the n's, right?
Yeah.
What do I need to factor out of here? A negative 1 to the n, right? So let's do that. So I have negative 1 to the n plus 1, negative 1 to the n, 2 to the n, over n, 2 to the n. Okay, so what happens to the 2 to the n's? They cancel. When you multiply like bases, what are you supposed to do with those? Add the exponents, right? So this becomes the sum from n equals 1 to infinity of what? Negative 1 to the 2n plus 1 over n. No matter what I plug in for n, what kind of power is that going to be?
Negative.
Or off.
odd. No matter what I plug in for n, that power will be odd. -1 to an odd power will always be negative. That is a divergent p-series. Therefore, 3 is not included. Following me? Okay, stay with me. We got one more to do. So now I have to do at x equals 7, right? Are you caught up with me? Okay. So at x equals 7, I have the limit, the sum from n equals 1 to infinity of -1 to the n plus 1 times 7 minus 5 to the n over n 2 to the n.
This one's easy. It's over into
Question?
Maybe it's-
It'll just be like a positive version of the other one. That's what it looks like.
Well, careful. Let's keep going. I have -1 to the n plus 1, 2 to the n over n 2 to the n. The 2 to the n's cancel. So now I have the sum from n equals 1 to infinity of -1 to the n plus 1 over n. Now what does this series do? It alternates, right? It alternates because it's the power goes from even to odd, even to odd, even to odd. So the series is going to alternate. Anytime a series alternates, I do the what? I do the alternating series test, right? So the alternating series, it asks you to do the limit as n goes to infinity of 1 over n, and it asks if that equals 0. Does it? Check. And then it asks to make sure that it's decreasing. Well, the derivative of 1 over n is -1 over n squared, which is always less than 0, so check. So this is a what? This is a convergent, and like Dalton pointed out, it's actually conditionally convergent because it's 1 over n if you left off the -1, right? So that conditionally converges. So the interval of convergence is what?
3 non-convergence.
3 to 7. And what's the radius of convergence? 2. And how'd you come up with that, Parker? Okay, well, yeah, the other thing you can go back to, just go back to the original series, right? It's centered where? At 5, right? So you'd go 3, 7, so that's 2.
Do we have to say that 7 is included when we did the alternate series test?
That's what that.
I feel like.
Oh, like over here? No, no. And I just was showing this. I was trying to show every single step so that whenever you go to do this and when you're going back to look at notes, you can see it all. Okay, so your homework is going to be Larson 9.10, 5 through 17 odd. And you have that piece of paper on your desk already. There isn't any.
Oh.
Oh, you have to make sure it's decreasing. You have to make sure the limit of the term generator goes to 0, and you have to make sure that the term generator is decreasing.
No, you're, whenever,